Today, we are diving deep into a fascinating patent for a sensor that can essentially feel a single type of molecule in the air. Now, this isn't just a simple upgrade on old tech. It's a whole new way of seeing the invisible, and it's powered by the seriously strange rules of quantum physics. So let's break down European patent EP3537140B1. Okay, so here's our game plan. First, we'll look at the old-school problem this sensor was built to solve. Then, we'll get into the amazing quantum dot solution. After that, we'll explore the physics of how it all works, check the data to see if it actually holds up, and finally, we'll talk about what this could mean for all of us. All right, so every great invention starts with a problem, right? So what's the big challenge that this new sensor is designed to tackle? This is really the heart of the issue. How do you accurately measure something like carbon dioxide in the air instantly without all the baggage that's held back older technology for years? Just take a look at this comparison. The patent itself points out all the issues with what are called conventional NDIR sensors. They are total power hogs, and they need a long time to warm up. For anything that needs an immediate reading, like a critical safety system, that's a huge deal breaker. So how do you fix that energy and time problem? Well, the inventors turned to something unbelievably small and incredibly powerful. Okay, so this diagram from the patent shows us the guts of the device. At its core, it's a special kind of electronic switch, a transistor. You can think of it like a tiny path for electricity. But the real game changer is that layer right on top, the one labeled 160. That is a layer of quantum dots, and trust me, that's where all the magic happens. So what in the world are quantum dots? Well, think of them as artificial atoms. They're semiconductor crystals that are so tiny, their electronic properties are actually dictated by their size. That means by just changing how big the dot is, you can precisely control its energy levels. This ability to tune them, well, that's the secret sauce to this whole invention. Now for the really cool science. How does a layer of these tiny dots actually feel the presence of a specific gas molecule, like CO2? The answer is a really beautiful physics principle called resonance. You see, this whole thing comes down to a perfect energy match. Every molecule, including CO2, naturally vibrates at a very specific frequency. The inventors brilliantly tuned the quantum dots so their own internal energy level perfectly matches the vibrational energy of that CO2 molecule. When they match, energy literally jumps from the gas molecule to the quantum dot. It's kind of like hitting a C sharp on a piano and hearing a nearby guitar string, also tuned to C sharp, start humming all by itself. It's a perfect energy handshake. Okay, so this quote from the patent tells us what happens next. That energy transfer creates a tiny electrical change on the surface of the quantum dots. This, in turn, affects the current flowing underneath it in the transistor. The result is a measurable shift in what's called the threshold voltage, which is basically the amount of juice you need to flip the switch. That resonance is the trigger the sensor's waiting for. Now, to make the sensor super sensitive, that path for electricity has to be perfect. The patent suggests using a material called IGZO, which you can think of as a superhighway for electrons. It lets them move incredibly fast and freely. This means that even the faintest electrical change caused by the resonance can be detected instantly. Here's another clever little detail, making sure the signal is crystal clear. Quantum dots usually come coated with these long, dangly molecules called ligands, and these can actually get in the way and block the electrical path. So the inventors came up with a simple solution. Just swap them out for shorter ones. It's like clearing a bunch of roadblocks to create a clean, strong signal. Okay, so that's the theory. It all sounds great, right? But does it actually work in the real world? Well, the patent includes the data to prove it. Let's take a look. All right, here's our starting line. This graph shows the sensor's electrical behavior in just clean air. I want you to pay attention to that little point on the horizontal axis labeled VT. That's our threshold voltage. As you can see, it's sitting just under 4 volts. This is our baseline. Now, watch this. The second CO2 is introduced. That whole curve shifts to the right. And look at our threshold voltage, VT. It's jumped to a value clearly above 4 volts. That shift is the direct result of the resonance we talked about. It's the unmistakable, measurable signal that the sensor has detected CO2. No ambiguity about it. And what happens next is just as crucial. When the CO2 is taken away, the graph snaps right back to where it started. The threshold voltage goes back down below 4 volts. This is huge because it proves the sensor isn't a one-and-done device. It's reversible, it's stable, and it's ready to take another measurement, which is exactly what you need for any kind of real-time monitoring.
So we have the problem, we have the quantum solution, and we've got the proof that it works. So what? What does all of this actually mean for the real world?
The potential here is absolutely enormous. Just imagine tiny, super low power sensors that you can tune to detect pretty much any gas you want just by swapping out the quantum dots. We're talking about real-time air quality monitors in every room, or safety systems in factories that can instantly sniff out a dangerous leak, or maybe even new tools in healthcare. So what exactly does this patent protect? Well, it's not just the device itself. It's the specific method of using this layered structure, where those quantum dots are precisely tuned to resonate with a target gas. The real heart of the invention is applying this incredible resonance principle to the problem of gas detection. And that leaves us with a massive question, doesn't it? This patent is focused on CO2, but the very same principle could be applied to countless other molecules. So if you could create a tiny, cheap sensor for practically anything just by tuning some quantum dots, what's next? Could you build a device that can smell a disease on someone's breath? The possibilities, they're really mind-boggling.